Well, hello one and all, and welcome back to CS50's Introduction to Programming with R. My name is Carter Zenke, and this is our lecture on applying functions. We'll take a look at functions in particular, writing some of our very own, and we'll also learn about loops, how to repeat certain segments of code over time. Towards the end of lecture, we'll combine these two ideas to dip our toes into this thing called functional programming. So let's begin. Let's start by actually looking at another program we had from before, one called count.R. And if you remember, this program was designed to count up some number of votes we typed in the console. So if I click source here, I can run this program, and I'll enter in 100 votes for Mario, let's say, and 150 for Peach, and 120 for Bowser. And I'll see that all in all, I typed in 370 votes. So this same program from before. And I'd argue this program is correct. It works just fine. But there's an opportunity for improved design here. I could write this code a little bit better. And one thing I notice in particular is on lines 1, 2, and 3, I'm repeating some functionality over and over and over again. I'm asking the user for some input, converting that to an integer. I'm doing the same thing on line 2 and the same thing on line 3. And when you find yourself repeating this kind of functionality over and over and over again, it's a good clue that defining your own function might help you. So we want to define a function here, but how do we do so? We've certainly used functions before, but to create a function is something else entirely. Well, to create a function in R, we're going to use this keyword called function, followed by some parentheses. Now, you might also think, well, I want to give this function some kind of name that I could reuse throughout my program. So to give a function a name, I could use this syntax here. Maybe getVotes is assigned this function here. So getVotes now will be the name for my function because I want this function to, let's say, get some votes from the user. Now, this is pretty good. We have a name for our function, but what we'd also probably want is the ability for our function to take some input, some arguments, and run with those arguments. So if I wanted to change how my function runs, I could supply parameters inside of these parentheses here. I could supply any number of them separated by commas. But then, even with a name and some parameters, our function needs to do something. So to specify what our function actually does, we'll use these curly braces here in which we can define our function's body. That is, the lines of code that will run when our function is run. And down below, towards the end of these curly braces, we'll say what our function should return to us, the programmer, after it finishes running. So with this syntax here, let's actually go ahead and define our very own getVotes function that can ask the user for some number of votes. I'll come back to RStudio here, and let's write this function called getVotes. I want it to have the same functionality, essentially, as what I'm doing on lines 1, 2, and 3 here. But to define it, I'll first do so at the top of my program here. So I define it first and foremost, and then I can use it later on in my program. So I'll type, like we saw, get_votes. That's the name of this function. And I'll assign it to be some new function here. And I'll provide a function body just like this. So now I have my very first function in R, albeit an empty one, right? So I want this function, again, to get some votes from the user. So inside these curly braces, inside the function's body, I should define what code I want to run when I call or when I use this function later on in my program. Well, the thing I want to do is very similar to lines now 5, 6, and 7. I want to maybe ask the user for an integer, prompting them with something like, let's say, just enter votes for now, just like that. And I'll maybe assign the result to this object called votes that is now visible inside of this function for me. And once I get those votes from the user, well, I want getVotes to return them to me, the programmer, so I could assign them to some object like Mario, Peach, or Bowser down below. So to return some value from a function, I can use the keyword return, and inside parentheses say which object's value I want to return. So here, in total, is now my function. On line 2, I'm asking the user to enter some votes, converting that to an integer and storing it in this object called votes inside of this function. And then on line 3, I'm returning the value of votes so I can reuse it later on in my program. So now, I think I've implemented lines 6, 7, and 8 here as its own separate function. I should feel free to use that function now. On line 6, I'll actually not use as.integer and read line. I'll instead use get_votes and call it using these parentheses here. I'll do the same for line 7, get_votes, and line 8 as well. And now, before I run this program again, let's walk through top to bottom what I've just done. On line 1, I have defined this function called getVotes. I've told R exactly what inputs it takes, in this case, well, none. I've told R exactly what it should do when I call this function, first line 2, then line 3, and I've given it some name, getVotes here. So now, on line 6, 7, and 8, I can call getVotes. And every time I do, R will effectively go back to these lines 2 and 3, run those, and return to me the value that I've asked it to return for each of Mario, Peach, and Bowser. So now let's run our program. I'll click source here and enter in some number of votes. I think we had 100 first for Mario, so I'll say 100, and then 150 for Peach, and 120 for Bowser. And now I see the same functionality, but now in my own function. So congratulations, this is your first function in R. But if I'm doing this, I actually think I have lost some functionality, because if I run this program again, I'll see enter votes. And before, we had this nice ability to prompt the user with some particular prompt that we wanted to. So how could we get that back? Well, one thing we could define now is a parameter to this function, some input that changes how it runs. And as you saw, we can define those parameters inside these parentheses here after our function keyword. So one thing I want to do is be able to change the prompt that I prompt the user with. So I'll call this parameter prompt, just like this. And now my function can take this input called prompt. Well, when I do that, maybe I also want to use that particular prompt the user has entered, that I, the programmer, have entered as the input to get votes, and prompt the user with that instead. So now inside this function, I have access to this parameter, this argument called prompt, that I can then use to prompt the user on line 2 here. So let's try this. I'll now give as input to this function Mario, like we had before, and Peach, like we had before, and Bowser, like we had before. Each time I call this function, I'm setting this character string Mario equal to prompt, and then prompting the user with that prompt now. Let's see what happens. I'll click on source, and now, instead of enter votes, I'll see Mario. I'll type in 100, 150, and 120, and I'll get back the same result. So pretty handy here to be able to define parameters for our functions and change them over time. Now, one optimization still we could make is that on line 3, I'm explicitly returning votes from this function, but it turns out that in R, by default, the last computed value, in this case votes, will be returned automatically for me. So on line 3, I actually don't need to explicitly say return votes. I could omit that, and R will, by default, return the last computed value inside this function, which is votes. So stylistically, we often want to avoid typing return when R by default actually does that for us for the last computed value here. Let me run this program again. I'll click source. I'll type 100 votes for Mario, 150 for Peach, 120 for Bowser, and now we're back in business. We have 370 votes in total. Now, let's say I get a little bit lazy as a programmer, and maybe sometimes I forget to enter in some value for this parameter we defined called prompt, right? I could go back to what we had before, using these functions without any input. But now, because my function is defined as taking this parameter called prompt, I think I might run into some trouble. If I click source here, I'll see I get an error. Error in get votes. Argument prompt is missing with no default. So if you're defining a function and you want the user or the programmer to need to define some argument to that function, well, you're going to need to do exactly what we did here, where if I define this parameter and don't give it a default, the user or the programmer must supply some value for it. But if I'm being a little bit nice and I want to maybe catch somebody doing this and provide them with some default value, I could do that too. Up here in function, I could say prompt and give it some default value. Maybe set it equal to, initially, enter votes, just like this. So now, if me or somebody else doesn't provide some input, well, the default value for prompt will be enter votes. Let me try this. I'll click on source, and now I'll see no error. I instead see enter votes. So even though we didn't supply some input to get votes here, we defined some default value that is used instead. So prompt, when there's no value supplied, is going to be equal now to enter votes, as we've seen down below. So pretty good. If I want to override this, as I might often want to do, I could do it as follows. I could go back to what we did before and type in some input, like Mario, or like Peach, or let's say like Bowser, just like this. And because this is the first input I've given to my function, and prompt is the first parameter, well, Mario will override, let's say, the default value of prompt, and same for Peach, and same for Bowser. There are a few ways to supply arguments to functions we've seen so far. One is positionally. Here, notice that the very first argument to get votes becomes the value for the first parameter, prompt. If, though, I had more than one parameter and more than one argument, I could define them separated by commas. So maybe this would be my first argument here, Mario, followed by a comma. I could then provide some other value for the next argument if I had one in my function here. But I don't, so I won't. The other way I could define the argument for a particular parameter is by actually using the parameter's name. So this name of this parameter is prompt here. I could override that and make sure to explicitly say that this prompt is going to be equal to Mario using syntax like this. I could say that getVotes I know explicitly has this argument parameter called prompt that I'll set equal now to Mario. And same for Peach, and same for Bowser. So now I'm able here to run this code by supplying or overriding the default value now of prompt. So I think this is a pretty good first function. If I click source and I click run, I can do 100 votes for Mario, 150 for Peach, 120 for Bowser, getting that total back. But what's interesting that I notice now is if I go to my environment on my right-hand side, I'll see a few different objects that I have. I see Bowser, I see Mario, I see Peach in total, I see getVotes, the function which we defined, but what I don't see is this votes object, or prompt. And actually, if I go down to my console and ask R to give me the value of votes as it currently is, well, I'll see error, object votes not found. Now, why is that? Well, this has to do with what we call in programming this idea of scope. And scope tells us in what context objects like these are defined. To visualize this, let's think about our environment here and think about what scope we have in terms of our objects in that environment. So here is a representation of our environment. We have those 4 objects we saw earlier. Mario, Peach, Bowser in total. These are accessible to me, the programmer, pretty much at all times. We also have, of course, our function getVotes. But getVotes is kind of best viewed as this black box. I don't exactly know what's going inside of it when I call that function. If you think about calling a function like sum or mean, you likely don't know exactly what code was defined to compute those values. You just know that it kind of works. You give some input and you get that output back. Well, the same thing now with our own functions. We just have to trust that we ourselves have defined these functions to take some input and produce an output for us, and we, the programmer, can actually access those objects we defined inside the function. If we want to use those, we need to kind of metaphorically zoom in or go inside that function's context to then be able to use and see those values, like votes and prompt. But for our sake, as the programmer, these objects are only defined inside the scope of now our function, which is why we can't see them in our global environment, as we saw in R. So we have now defined our first function. We've taken in some inputs, we've returned some values. We've also seen this question of scope here. Let me ask what questions we have so far on scope or on defining our own functions.
What if the user enters a string or a character as an input? Is there any way to handle the errors that we'll get?
Yeah, really good question. So up until now, we've been kind of being a good user. We've been supplying numbers to the actual program here. But we need to think defensively as programmers and think about what could happen if we entered in something that wasn't a number, for instance. So let's see what might happen here. I'll come back to my computer, and let's go back to our program called count.R. And let me close my environment. But now, think a little more maliciously as a user. What could I do to break this program? Well, one thing I could do is enter in some value that I don't think the program expected to see. So if I click source now to run the program again, let me enter in something funny like duck for Mario, or quack for Peach, or cat for Bowser. And these are certainly not numbers. So if I hit enter now, ooh, this is some pretty bad output. So what I see down below is total votes is now equal to NA, this value that means not applicable. And I see some warning messages. Now, if I look at this particular one in get votes prompt equals Mario, NA is introduced by coercion. Well, what does that mean? Well, we saw a little while ago that coercion is this process by which we convert some storage mode to some other one. And it seems like we do that on line 2 on as.integer. We convert some character string the user gave us via readline to some number or some integer in particular. But what might happen if I did something like I did here? I gave cat instead of an actual number. Well, as.integer will say 1. I don't know what the heck you want me to do with that, so I'll give you NA instead. And it will also give me what's called a warning, telling me that, look, I couldn't do what you wanted me to do with the input you gave me. So this is why now we see this value NA as opposed to, let's say, cat or duck or quack instead. So what can we do to fix this? I think one thing we could do is try to catch this process. Like if we see inside this function that we actually gotten an NA value for votes, well, we could return something else entirely. We could start there. So let's go back to our program and make that happen for us. We could use what we saw last time called conditionals, where conditionals let us test for something and take some particular action because of that test. So here, let's assume the user enters in some bad value, like duck. And now votes is NA. I don't want to do what we did before, which was return votes automatically. I'd rather first ask, is votes NA? And if it is, let's go ahead and not return the actual NA value. Why don't we return something like 0, maybe, just to kick things off? If I say if now, if votes is NA, well, then inside, I could return some special value, like 0, saying that, look, we couldn't count your votes. But otherwise, let's say, we could go ahead and safely return votes. So if votes is not NA, we can go ahead and return votes instead. And I think this will be a little bit safer for us. If I go ahead and click on source now, let me go ahead and type in duck for Mario, quack for Peach, and cat for Bowser. And so I seem to have gotten total votes being 0. Like that's a little bit better. It's no longer NA. We seem to have just not counted like cat, duck, or quack. But I still get these warnings. Now, these warnings we'll see a little bit more depth in a future lecture. R does have warnings and errors that are more generally known as exceptions, but for now, we can handle them using a function called suppress warnings. Suppress warnings allows me, the programmer, to say, look, I know something went wrong, but I'm handling it myself. I know how to do this. So let's see if we could tell as.integer to not give us a warning anymore, because we're handling it a little bit later. Let's come back to RStudio here. And I could use, like we said, this function called suppress warnings, where suppress warnings takes as input a function that could give us a warning, in this case like as.integer. So now, if I give as input this particular function, like this, suppress warnings, what I'm effectively saying is that as you take the user's input and you convert it to an integer, if you encounter a warning, don't give me that warning. Just kind of suppress it, keep it low, and I myself, the programmer, will handle it later on as well. So let's try this now. I'll click source, and I'll do 100 votes for Mario, 150 for Peach, and 120 for Bowser. And I think now we're back in action, although that was some good input. So let's try the bad input. Let's go ahead and do duck for Mario, quack for Peach, and cat for Bowser. And now we see total votes being 0, but now no warnings being raised thanks to suppress warnings. So we'll see this in more depth in a future lecture. But for now, just think about suppressing those warnings, kind of silencing them, because we, the programmer, know how to handle those in our own code. Now, there's one more improvement I see here, which is that this block from line 3 to line 7, this if-else, could be simplified, could be converted to one line of code. And in fact, if you have an if-else statement, where inside the if and inside the else, you're simply returning one value or another, well, you could simplify this and use a function called if-else, just like this, where the first argument to if-else is the logical expression to test. In this case, is votes NA, just like this. And if that expression is true, if votes is NA, well, the second argument will be the thing we return, the value we get back from if-else. And then the third argument will be what we get back if this logical expression is false. It's the else in if-else. So I'll say votes here instead. So now, to be clear, line 3 is doing exactly the same work as lines 5 through 9, but it's much shorter, I would argue more readable, and so I can now get rid of lines 5 through 9 and shorten this function even more. And because R will return to me the last computed value, if else, whatever it returns will be the return value of my function itself. So if votes is NA, if else will return 0, but so will my function, and same with votes as well. So let's try this again. I'll click source, and let me go ahead and say something like duck for Mario, but I will enter in maybe 150 for Peach and cat for Bowser, and now we see our total votes is 150. And I think we've really simplified this function for ourselves here. Now, as we've done this, I think you're seeing the power of putting this functionality inside of a function. If I hadn't done this, if I had had to repeat this code over and over and over again, my code would have been much longer. You could imagine myself repeating that same conditional, if else, if else, if else, through all my prompts to the user. But by converting that code into my very own function, I can modularize things. I can make things easier to maintain and to update, which is why in the first place we would write functions like these. So we've seen how to write our very first function in R to handle some errors our user could present us with. What other questions do we have about defining these functions?
If we had the first version of our function get votes and that we were still not checking for NA values by version, would we need to actually store our computation in the votes object, or could we just return the value directly?
Yeah, a really good question. I think something gets at shortening this program even more. If we go back, rewind a little bit to maybe not handling these NAs that could be introduced, but instead just returning, let's say, whatever the number the user gives us is, I could probably shorten it even more. So let me go back to RStudio and show you what that could look like. I will maybe get rid of this if-else here, and I'll instead maybe do this. I'll go back to what we had before, which was assigning this object votes whatever number the user types in. Now, I think you were asking, could we just get rid of this object votes? Could we simply have this, as.integer, read line, given some prompt? I think we could, because as.integer will still return for us whatever number the user has typed in, and therefore, because it's the last line of my function will instead return that value as well. So I'll click on source to run my program. I'll type 100 for Mario, 150 for Peach, and 120 for Bowser. And now I see the same result we wanted. I would argue, though, because we want to keep this value and test its actual its value later on, like was it NA or was it a number, we might want to actually store it in a separate object and then test that value a little bit later, like we did here. But a great question and a good optimization, too. OK, so our program is better. Like, it's certainly better than it was before. But there's still one thing I think that's missing, which is if I click source now and I type in maybe quack for Mario, I've missed my chance now to enter Mario's votes. Wouldn't it be nice if instead my program could reprompt me every time to enter in a number for Mario, and it won't stop, let's say, until I do comply. I enter in the number for Mario's votes. Well, for that, we'll actually need some new structure, one called a loop. And in just a few minutes, we'll come back and talk about how to implement these loops in our code. We'll see you all in 5. Well, we're back, and as promised, we're going to learn together about these things called loops. These structures let us repeat some code some number of times. Now, for this, I brought along a friend, the CS50 debugger, which is great to talk to about my code, just about the illogic in my thoughts, but also great for thinking about loops. In particular, if you have a duck or any kind of object to squeeze, you can use that to think about how loops work underneath the hood. So let's go ahead and jump in and see what this duck can teach us about loops. So if you come back to my code over here in RStudio, I have a program that kind of simulates me squeezing this duck 3 times. For instance, like this. It's a bit more of a squeak than a quack, but we'll go with it for now. If I type source here, click source, I'll see quack, 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 me squeezing this duck now 3 different times. So putting what we just did physically now into text. So let's visualize this code in terms of a flow chart and see what it looks like. Well, here at the top of my program, I start it. I click source, my program begins. And the next step then is to say quack. Every arrow now indicates some next step in my program. Well, after I say quack 1 time, I squeeze once. What will I do but say quack again, just like this. And I'll quack again, just like this. And now I'm at the end of my program. I stop entirely. But let's say I want to quack my duck or squeeze it more than 3 times. If I have only this to work with, what might quickly become my problem? If I want to do this 5 times or 10 times or even more, well, I'd probably need to do a lot of copying and pasting. If I can come back to my code here to show you what I need to do, if I want to simulate squeezing this duck not just 3 times, but 5 or 6 or 10 or more, well, I need to copy line 3, put it on line 4, copy line 4, put it on line 5, and so on and so forth to repeat this code some number of times. Now, thankfully, we don't have to do this in R. And in fact, as programmers, you should be looking out for cases like these and thinking, I could probably use a loop instead. So let's see what kind of loops R offers us, what kind of keywords we could use to make a loop and to repeat this code some number of times. Well, one of the first loops we have at our disposal is one called repeat. Repeat allows us to repeat whatever code is inside of its curly braces infinitely, however many times we want it to. So let me go ahead and go into my RStudio again, and I'll type repeat now, this keyword, and I will then, inside of those curly braces, put this function cat, which will print to the screen, quack. And before I run this code, let's visualize its flowchart to see how it might work. Well, here on my screen, I have this program. I'm going to start that program, and then I'm going to quack, or squeeze my duck. And then I'm going to follow the arrow and quack, just like this. And then I'm going to follow the arrow and quack, just like this. And I'm going to go follow the arrow again. And I worry I might be stuck here for a very long time, because it seems like our next step is always to go back and to quack and to quack and to quack again. So before we dive into fixing this, let's talk about a bit of vocabulary. Now, what we've created here is in fact a loop. We're repeating this code over and over and over again. Now, each time we repeat this set of code, we're calling that one iteration. So in other words, when I loop again and again and again, I'm iterating again and again and again. One iteration means one segment of my code, top to bottom, inside of that loop. And I think what we've created here is something called an infinite loop, one that will never ever end, because there's no condition telling us when to stop looping. So we'll need to figure out how to break out of this kind of loop and figure out what we could do to get out of it. Now, thankfully, R does offer us some keywords to do just that, so let's explore them now in R. I come back to RStudio, we'll want to introduce these two keywords here, break and next. Break symbolizes breaking out of some loop. When R encounters that break keyword, it will end that loop entirely. It will stop wherever it is and end that loop. Next, on the other hand, says wherever you are in this iteration, go ahead and start the next iteration from the top. So let's try these out now in R. If I come back to my program, duck.R, I don't want to repeat this quack over and over and over again, but let's say I do, maybe accidentally, I click source now, and whoop, my computer is just stuck saying quack, 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 quack over and over infinitely forever. I could, if I wanted to, exit this program if I type Control-C. That means stop this program, whether we're in a loop or we're not. So that can save us, Control-C, but ideally, I should consider a stop condition before I go ahead and repeat something infinitely many times. Now, what could I do if I wanted to quack, let's say 3 times? One thing I could do is think about counting, like maybe on my fingers. If I want to quack 3 times, I could maybe start at 3, and if I have 3 here, I could quack. I could go down to 2 and quack again, go down to 1 and quack again, and then finally, at 0, I'm done. I shouldn't squeeze my duck anymore. So one thing we could do is try to put this idea of counting now in code. Well, I could create an object to store the number of times I want to squeeze this duck. I could, by convention, call it I, and that will keep track of the number of times I want to iterate in this loop. So on line 1, I'll say I'm going to assign this value I to be 3. It's kind of similar to me holding up my hands and saying 3 fingers, for instance. And now, as I repeat this code, I don't want to repeat it infinitely. I want to have some condition under which I break out of this loop. And as we saw before with my fingers, maybe the condition is if I is equal to 0, well, at that point, I want to break this loop. I want to exit it and not loop anymore. But I shouldn't run this code just yet, because while I've set I equal to 3, like I have on my fingers here, what I haven't done is made a mechanism for actually dropping fingers, going from 3 to 2, from 2 to 1, from 1 to 0. So maybe after I quack, I'll go ahead and adjust the value of I. all set it equal to I minus 1, just like this. And then let's say maybe in the case that I is 0, eventually we're going to break out of the loop. But if it's not, why don't I go ahead and go to the next iteration? When we see the next keyword, we'll stop our current iteration and go to the top again to repeat our code, top to bottom, just like this. So the flowchart for this code looks a bit more like this. I'm going to start my program, and I'm first going to set I equal to 3, kind of like I did on my fingers here. Then I'm going to squeeze the duck, going to quack, subtract 1 from I, and ask a question. Is I equal to 0? If it's not, well, I'll go back up and I'll squeeze the duck again. I'll subtract 1, ask that same question, and if I ever get to ask that question and the result is true, well, then I'll stop my program. So let's visualize this here using some interactive stuff. I have my iPad here that can count, let's say, from 3, just like this, oops, 3, down to 0, let's say. So currently, when I is 3, what do? I squeeze my duck once, just like this. I'll then subtract 1 from I, where I is kind of this iPad here, where I subtract 1 now, and now I is 2. I'll go back up and I'll squeeze again. I'll subtract 1 from I. Now I is 1. I'll ask the question, is I equal to 0? It's not, so I'll go back up again. I'll squeeze the duck one more time, and I'll subtract 1 again, and now I is equal to 0. So we'll stop our program. There will be no more squeezing of this duck. So this is one way to approach the problem of creating some loop and having it repeat a certain number of times. But R comes with other kinds of loops too. A repeat loop is great when you want to do something at least once. I want to squeeze this duck at least one time, but if I only want to do it if some condition is true, or while some condition is true, I could use another kind of loop as well. This loop is called a while loop. A while loop lets us repeat some set of code while some condition is true. So let's see what that looks like now in R. I will remove what I currently have and instead implement this while loop. So if I want to make a while loop, I can use while, just like this, and I'll make a condition to repeat under. As long as this condition is true, I will repeat the code inside this while loop's curly braces. So I could say maybe while I is not equal to 0, I want to repeat whatever code is inside of this while loop. Well, I want to quack, so I'll say cat quack, just like before, \n, make a new line, and then why don't I go ahead and add back this kind of helper object I had called I. I is assigned the value 3, and after I quack, well, I'll subtract 1 from I just like this. I is now assigned the value I minus 1. So a bit shorter than our repeat loop, but I argue it would do the same exact thing now. So let's visualize what's happening in this program. Well, the first thing we do is we set I equal to 3, just like this, and then we ask the question. Before we do anything else, we ask the question, is I not equal to 0? If it's not equal to 0, if that is true, we're going to squeeze our duck and subtract 1 from I. And then we'll ask the question again. Is I not equal to 0? And if ever in our loop that question is false, that is, this condition is no longer true, we will stop, exit our loop entirely. So let's visualize this now. I was first set to 3. So I'll set I here to 3. And now the difference is, before I do anything, I'm going to check this condition now. Is I equal to 0? Or is I not equal to 0? Well, I is 3, so yes, I is not equal to 0. I'll go ahead and quack, just like this, and I'll subtract 1 from I. Now I'll go back to the top of my loop and ask that question again. Is I not equal to 0? Well, I is 2, so it's not equal to 0. I'll go ahead and squeeze my duck, subtract 1 from I, and then ask the question again. Is I not equal to 0? Yes, it's not equal to 0. I'll squeeze, subtract 1 from I, but now when I ask the question, is I not equal to 0? Well, I is not equal to 0. In fact, it is 0, so I will exit my loop altogether, squeezing my duck now 3 times in total. So let's visualize this. I'll come back to RStudio now, and if I run this code by clicking source, I will have quacked exactly 3 times, counting down from 3, 2, and 1. OK. So just as we have counted down, we could also imagine counting up. Maybe I start I at 1, And my condition now is to loop so long as I is less than or equal to 3. Like I could imagine 1, 2, 3 times, but not 4. So I'll say, while I is less than or equal to 3, I want to keep quacking. But now I need to actually increase I as I go on each iteration of my loop. On each run from the code, top to bottom, I want to increase I by 1. And now let's visualize what this is doing in terms of a flowchart. Here, very similar idea, but we're starting now from 1. I equals 1, and we'll ask this question. Is I less than or equal to 3? If it is, we'll squeeze our duck and add 1 to I. If it's not, as we go back and approach that question again at the top of our loop, if it's ever not the case that I is less than or equal to 3, we'll stop. We won't loop anymore. So again, let's visualize this. But now I is first set to 1. So before we do anything, we ask the question, is I less than or equal to 3? It is. We'll squeeze our duck, add 1 now to I, and ask the question again. Is I less than or equal to 3? It is. I'll squeeze, add 1 to I. Now it's 3. Is 3 less than or equal to 3? Well, it's equal to, so I'll go ahead and squeeze, add 1 to I, and well, now it's 4. And 4 is not less than or equal to 3, so we'll go ahead and stop our loop and not loop anymore. I'll come back now to RStudio, and I will show you what this looks like now. If I click source, I'll see quack, 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 again quacking 3 separate times. So we've seen now 2 kinds of loops in R, one called a repeat loop and one called a while loop. Let me ask, what questions do we have about these loops so far?
How could we decide when to use repeat or when to use while, or it doesn't matter?
Yeah, really good question. So in general, as we'll see, a repeat loop tends to be good when you want to do something at least once. You want to quack at least once. You want to prompt the user at least once, and then check if you should repeat or not. A while loop is good if at the very beginning, before you do anything else, you want to check some condition, and you want to repeat that code while some condition is true. So you could think of a repeat being like, do this once, but then check if you should do it again, whereas a while loop is more like, if our condition is true, we should be repeating this code over and over again. Really good question there. All right, let's keep going. And one more loop we have available to us in R is one called a for loop. A for loop lets us do some piece of code for each element in some list or vector of elements. So instead of now using the while keyword, I could use the for keyword. I could say for, and it turns out that inside of the parentheses of a for loop, I need a few different components. I need still some kind of helper object to keep track of each iteration, but I also need some vector of elements to do some piece of code for each vector in that element, or each element in that vector, sorry. So I'll say for I in, and then have a vector here. Let's say 1, 2, and 3. And now I have, the same as before, my body of this loop, where inside of it, I want to quack just like this. Now notice there's no need for me now to increment or decrement I, to add or subtract 1, because this is all taken care of thanks to our for loop. What the for loop will do is first set I equal to 1, and then it'll say quack, and then set I equal to 2, and then quack again, and then set I equal to 3 and quack again. But then at the end of this vector, once there are no more elements to iterate over, well, our for loop is done. So I, as it iterates, kind of assumes the value of 1 and then 2 and then 3. And if I were to click source now, I would see quack, quack, and quack down here in my console. Now, I could simplify this just a little bit more. I could maybe make a vector that's going to be a little more dynamic than this. Like I can imagine myself typing in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to quack 10 times now if I were to click source here. But that's going to get really tedious if I want to quack more than, let's say, 3 or 4 times. So what I could do instead is use our syntax to give me some vector that is between certain numbers. So 1:10, for instance, would say, give me a vector that includes 1 through 10 inclusive, which I can show you in my console here. 1:10 gives me 1 through 10 inclusive. with this, could I actually change how many times I loop? If I click source, I'll see 10 quacks. If I change this to 1:3, well, now I'm able to see quack, quack, quack down here in my console. So a for loop is going to be the tool for you if you have some list, some vector of elements to loop over, and then you want to do some piece of code for each of those elements there. OK, so now we've seen the 3 kinds of loops in R. We've seen repeat loops, we've seen while loops, and we've seen for loops. Our next step will be to apply these same loops to improve the design of our programs. We'll come back in 5 and do just that. See you all soon. Well, we're back, and as promised, we're now going to explore how we could apply functions to make the design of our programs even better. So let's pick up where we last left off, writing this program called count.R. And we left off with this idea of wanting to re-prompt the user any number of times until they comply with whatever kind of input we want, in this case, a number. So we saw just a little bit ago that a repeat loop is a great loop to use when you want to do something at least once and then check if you should do it again or break out of the loop. Now, in this case, I do want to prompt the user at least once. I want to tell them to input some number at least once. If they don't comply, well, then I'll loop again, but at least I want to do it once. So I could use a repeat loop here, and I could use it in the same way we just saw, using the repeat keyword followed by some parentheses or some brackets just like this. And then inside those brackets, inside of this loop's body, I could be sure to prompt at least once just like this. I will ask the user for some number of votes and store it in this object called votes. But now, I don't want to run this code because this will make an infinite loop. I'll be constantly asking the user to enter in some number of votes, so I need some condition under which I would break out of this loop. And I think that condition might be if the votes we receive is not NA. If we get back some valid number of votes, that will be not equal to NA. If we do get some weird input, like duck, though, that will be NA, in which case we should keep looping. So let me ask the question, is votes, in this case, is it not equal to, is votes not equal to NA, just like this? And if it's not, well, we're going to break out of this loop. We're going to say, look, we're done. Votes is not NA. We don't need to ask the user anymore. Alternatively, if votes is NA, we could continue on to the next iteration. Now, there's one improvement here, which is that technically, when we get to the bottom of this repeat loop, get to its last curly brace in the body here, it will automatically go back up to the top, do the next iteration from the top of its body. So I'd argue that this extra next here isn't really needed. We're going to go to the next iteration regardless if we don't break out of this loop altogether. And now I think we have a good loop going. I'm going to ask the user for their votes. If, in other words, this is a valid vote, a valid number, we're going to break out of the loop, not prompt them anymore. And what can we do? Well, now we don't need to check if votes is NA, because if we get down to line 8, we know votes is not NA. I could simply return votes overall. So here I think is a better implementation, one that will prompt the user again and again until they enter some number of votes that we actually want. Let me go ahead and click source, and let me type 100 votes for Mario. But now, maybe I'll type duck for Peach, and I'm reprompted. OK, maybe I type quack for Peach. I'm reprompted. Maybe I'll now comply. I'll say, OK, 150 votes for Peach. And now we move on to Bowser. So this seems to be working here. I'll go ahead and type 120, and now I'll see my total votes was 370. Now, one more improvement is that it seems to me a little extraneous to break out of this loop and then return, because a return actually signifies that no matter where we are in our function, we're going to stop the function altogether and return the value we have. So it seems to me like I could move this return from line 8 to inside of this if statement. And now, if votes is not NA, if we have some valid number of votes, we'll not just break and then return, we'll go ahead and just simply return, because a return would, by nature, break us out of the loop anyway. We're going to stop this function altogether. So let's try this again. I'll save my program, click source. I'll type 100 for Mario, 150 for Peach, 120 for Bowser. And now I think we're in good hands if we have good input. But if I type source, let me go ahead and do duck for Mario. Prompt it again, maybe quack for Mario, maybe 100 for Mario. Now I think we're doing well with invalid input as well. So pretty good. One other thing we could do, though, is think about these lines, 10 through 12. Well, it seems to me like for each candidate that I have, I want to get some number of votes for them. Notice how I said for each candidate. Well, if we want to do something for each candidate, for each item in some list or some vector, well, a for loop might be a great tool for us here. Why don't I go ahead and try to make a for loop now? I'll say for, as we saw before, this helper object called I. For I in, well, I want to prompt the user for every candidate that I have. And although we just saw for loops being used with numeric vectors, vectors that include like 1, 2, 3, 4, and so on, we can also use for loops with non-numeric vectors. I could give a vector of the candidates that I have and know that a for loop will loop over each candidate in that vector. So I could do something like this. I could say for I in a vector of my candidates, Mario, Peach, and then Bowser. And then I'll provide the body of this for loop. Now, what do I want to do in this loop? Well, each loop, I will first be assigned some new element to my vector. First it will be Mario, then Peach, then, not Bowser, just like this. And then I want to, in this case, ask the user for some number of votes on each iteration. First for Mario, then for Peach, then for Bowser. So I could probably simply call get votes, just like this, and maybe store it in some object called votes, like that. But now the question is, how would I show the user the right prompt? Like, I can't type in Mario here, because then Mario would show up with a prompt on every iteration of my loop. I need to make it more dynamic than that. One thing I could do is take advantage of how this object I is actually assigned the value of each element on each iteration. So on the first iteration, I will be equal to Mario. On the second iteration, I will be equal to Peach. On the third iteration, I will be equal to Bowser. So I think I could use that to my advantage. I could take the candidate name, let's say, and maybe add in dynamically this colon space with, let's say, paste 0, like we've seen before. I could say paste 0. I want to paste together the candidate's name followed by colon space. So now, on each iteration, I will first be equal to Mario. We'll get votes for Mario by prompting the user for Mario's votes. Then, on the next iteration, I will be Peach. We'll prompt the user for Peach's votes, followed by a colon space. And then the same thing for Bowser. So I think I could get rid of, let's say, this code down below here. But what am I left with? Well, it seems like on line 14, I was summing up Mario, Peach, and Bowser, but those objects don't exist for me anymore. I only have this one value now called votes, which seems to get changed every iteration. Like the first, it will be Mario's votes. The next iteration, it will be Peach's votes. The next, it will be Bowser's votes. What ideas do we have for how to solve this problem? Any ideas for how we could maybe count up these votes while we go through our loop?
First, I think we should put it inside the for loop or return the sum.
Yeah, so a good idea. Like, we still want to return their sum. And I like what you're thinking about trying to do this within the for loop. One thing that comes to mind is maybe trying to keep a running sum. That is, let's first get Mario's votes, add them to our total, then get Peach's votes, add those to our total, then get Bowser's votes, add those to our total, and at the end of our loop, we will have a total number of votes to count up. So let's see this in action in R. I'll come back to RStudio here, and if I can't have separate objects now for Mario, Peach, and Bowser, well, no problem. What I could do instead is start my count a little bit earlier. Maybe I'll set total initially equal to 0. So before I loop, I assume, well, there are 0 votes. But then, on each iteration of my loop, what will I do? I'll ask the user for some number of votes for the candidate, whether it's Mario, Peach, or Bowser. And then, down below, I'll add those votes to the total. I will update total to be, in addition to include the total plus the new votes we've received. So I think I could get rid of now line 16, and let's think through what this is doing line by line here. Well, first, total is 0. And if I go into my loop now, I will first be equal to Mario on this first iteration. So I'll prompt the user for Mario's votes and store them in this object called votes. Let's say it's 100. On line 13, I take this object called total and update it. I add Mario's votes to it. If Mario had 100 votes, total will be now 100. Then I'll move on. I will then become Peach, and I'll ask for Peach's votes now. Well, if Peach's votes is 150, on line 13, I'll again say 100, which is the current value of total, plus 150. That's the new value of total, so 250. And you can see how we're kind of keeping a running track of our number of votes for each candidate. We'll do the same for Bowser, and I think at the end of this we will have a total number of votes for every candidate. So let me go ahead and click source now, and I'll see if I type in 100 for Mario, 150 for Peach, and 120 for Bowser, we still now have our total, but now using this loop. So I'd argue we've made our program a little more efficient using these loops and easier to read, easier to change as well. Now, what questions do we have about this program as we've written it? We've added in a few loops, a repeat loop, and a for loop. What other questions do we have about this program? Seeing none so far, so let's keep going here. And one thing else we can do with these loops is think about how we could apply them to other problems. So one problem we saw a little bit earlier was this problem of working with a table of data that had our candidates' votes in it. So if you recall, we had a table that looked a bit like this, where for each candidate we had the number of votes they received at the polls, this physical location, and the number of votes they received in the mail. So it seems like Mario received 37 votes at the polls, the physical location, and 63 votes at the mail. But then our question was, well, how many votes did each candidate receive? That is, for each candidate, what was the sum of their votes? And then for each voting method, like poll or mail, well, how many votes did we receive overall in those columns too? So to visualize, let me grab my clicker over here. To visualize, let's say that we wanted to find Mario's total votes. Well, we would just sum up the row for Mario here. And then if we wanted to find the total number of votes we received at the poll or in the mail, we would sum up each value in these columns here. So notice how, again, we're saying for each candidate or for each column. We want to sum up those votes. We could probably use a for loop to accomplish this same task now. Let's go back to R and see how this could work. I'll come to RStudio, and let's make a new program, one that is called tabulate. Let me go ahead and I think I might have it open already. I'll click on tabulate here, and I'll see a blank file called tabulate.R. Now, my goal is to read in this CSV of votes that we have, one called votes.csv. So I'll use read.csv, and I'll try to open votes.csv. If you look in my file explorer here, you'll see I do have a file called votes.csv. Now let me click source here to run this program, and I should now be able to view votes, the data frame. So a similar thing to what we've seen earlier, but one thing is now different. Notice how in a prior lecture we saw we had a column called candidates. Well, now what we've done is we've decided that the row names for this data frame are the candidates themselves. So Mario is the name of this first row, Peach is the name of the second, and Bowser the third. This allows us to define our data frame as exclusively numbers. We could sum like 37, 63, 43, 107, and moreover, it allows us to better subset our data frame, as we'll see in just a bit. So let's say my goal at first is to sum up the number of votes for each candidate across both the poll and the mail. Well, in tabulate.R, I could start by doing that by making a for loop, doing something for each candidate. So I could say for candidate, let's say, in row names votes, just like this, and get a body for this loop. And what I've done here is I've decided that I no longer need to call this value I could call it candidate. I call it really anything I want to, and I could use that inside of my loop here. The other thing I've decided is that instead of defining a list of the candidates, like in this case Mario, Peach, and Bowser, I could be more dynamic than that. I could decide to tell R that it should tell me what my row names are, what my candidates are, and allow it to iterate over those. So I'll ask for the row names of the votes data frame. And if I actually see them down in my console below, I'll see that I get a vector of Mario, Peach, and Bowser. So the same structure for our loop now, but different ways of asking for a helper object to iterate with and an actual vector of, in this case, candidate names. So now we have a loop to go over every candidate's name. And our next goal is to find out how many votes each candidate received across all of their columns here. Now, the first thing to do might be to subset my data frame to figure out for each candidate which rows correspond to that candidate. Now, we saw last time ways to subset data frames using the subset function, but now that we actually have this row name being equal to the candidate's name, we can make this even more efficient. Let me visualize this for you here. If we have our data frame called votes, and I want to find all of Mario's votes, well, if Mario is the row name for one of my rows in my data frame, I could simply use the name Mario in the place I would normally put the row's index. For instance, like this. If I say votes, bracket, Mario as the character string, because Mario is the name of one of my row names, I'll then get back the row corresponding to the name Mario. And same thing with Peach, and same thing with Bowser. So we're very quickly now subsetting our data to find each candidate's rows and their number of votes across all the columns here. Let's come back and try this out. I will show you in the console that indeed if I do type votes, bracket, Mario, and then comma space to say I want all columns, but only the row associated with the name Mario, well, I'll get back a single row from this data frame that includes Mario's votes. So if I can do this, at least in my console now, with particular names, I bet I could do it in my for loop where candidate will stand in for any given candidate's name. First it will be Mario, then it will be Peach, then it will be Bowser on each successive iteration. So to subset this data, I could use votes, the data frame's name, followed by brackets, followed by the row name, in this case candidate, on each iteration updating, and then comma space, saying I want all columns for whatever row corresponds to this candidate's name on whatever iteration it is that we're on. So now that I have this working for me, I could probably put this into the function sum to get back the total number of votes across all the columns. If you give sum a data frame of one row, it will sum up all the values in that given row. OK, so now I seem to have the sum for each candidate's votes. But I still need some place to store it to look at it later. So one thing I could do is make this object called total votes, just like this. But what's the problem now? If I were to run this code top to bottom, what might I lose? And a question here is, what might the value of total votes be if I were to look at it at the very end of my loop? Any ideas here? Why can't I just leave my code like this? And what might be the last value of total votes, do you think?
Okay, the last value will be the sum of votes of the last candidate of the last one.
Yeah, the last candidate that we have in our list would be the final value of total votes. So let's actually test this out. If I go back to my RStudio here, and why don't I run this code by clicking source, and now let me check on the value of total votes, just like this. Well, total votes seems to be 120. Who had 120 votes? Seems like it was Bowser. But why is total votes equal to Bowser's total votes? Well, let's think about this going top to bottom through our loop. First, candidate is equal to Mario, and we'll subset our data frame to find Mario's votes. We'll sum those up across all the columns and store it now in total votes. But then we'll go on to the next iteration. Candidates will next be Peach, and we'll subset our data frame to find Peach's votes, sum them across all the columns, and effectively overwrite Mario's votes with Peach's. So now total votes is Peach's total votes. But then when Bowser comes along, well, Bowser will also overwrite Peach's votes. At the end of our loop, what do we have? Well, only one candidate's votes and not all of them. So it seems like we need some way of making a vector of these actual total votes. And we could do that using some new syntax in R. One thing I could do is initially make an empty vector, just like this, total votes, and set it equal to this, C, followed by some parentheses. This is that same C function we saw earlier, but it means the empty vector, nothing, at least at first. And then in my loop, I bet we could add to this vector so we get back at the end not any single candidate's votes, but a whole vector of their votes. Now we'll need some new syntax for this and some new feature we haven't seen yet in R. But let's visualize what we could do with that syntax. So here is a visualization of the empty vector total votes. There's nothing here because there's an empty vector right now. But if I wanted to add some new element to it, and not just add the element, give it some name too, I could certainly do that. I could say total votes, bracket, and the name I want to give this element, and then assign the value for that element. So if I want to add to this vector, total votes, an element named Mario that has the value 100, well, I could do it using this syntax here. Well, what if I want to later add Peach's votes? Let's imagine this is the next iteration of our for loop. I would say total votes, bracket, Peach. And that would then make a new element in my vector called Peach with the value 150. And same, let's say, for Bowser. On my next iteration, I will add Bowser's votes. And now, at the end of my loop, let's say, I now have a vector of Mario, Peach, and Bowser's votes all together now. So let's try it. I'll come back to RStudio here. And let's try using this process of adding named elements to our vectors. Well, on line 5, I might say that I want to add to total votes a new element whose name is, well, whatever the candidate's name is on any iteration. So I'll say total votes, bracket, candidate, meaning that whatever the candidate's name is on this iteration, I want to add a new element with that name. And I'll give it the value of the sum of their votes. So if I click source, and now I go ahead and inspect the value of total votes by typing in my console and hitting enter, I'll see a much better output. I actually see each candidate's name in my vector, and I see the value now that they were assigned. 100 for Mario, 150 for Peach, and 120 for Bowser. So what questions do we have about this program as it exists now?
Could we, instead of adding the total votes in a named vector, could we add a new column to our votes data frame?
We absolutely could. So we could decide instead to make a new vector and add that as a column to our data frame. Just depends on what kind of output you want to do. So here we wanted this output of a named vector, but we could change this to, let's say, not supply a name to each element and instead just add some new element after element, much like this. Let me show you that real briefly here. I'll come back to RStudio. And let's say I don't want to give it some name. I just want to kind of add in successive elements here. I could say total votes becomes the combination of the current state of total votes, adding in this new element here. So a little bit tricky to parse, but let's see what happens here. I'll click source, and I'll show you the value of total votes now, just like this. And what do I get back? Well, a total votes vector that is Mario's votes, then Peach's votes, then Bowser's votes. And I could, if I wanted to, add this as a column in my data frame. I could say votes total, let's say, and then I could say make that the value of this vector here. So now if I run source, so I click source, I should see that I have this new column called total. And effectively what I've done here is if I remove this part first, is I've decided to start with this empty vector. And then on each iteration, I want to take whatever is in that current vector and simply append or add on some new element, which will be the sum of the current candidate's votes. So on the first iteration, we'll add our very first element to this empty vector here. But then on the next iteration, we'll have a vector of one element, and we'll add in one more element. On the third, add the third, and the fourth, add the fourth, and so on. So a good way to add vectors together using C as well. I hope that helps. OK, so let's go back to what we had before here. Let me do Command-Z a few times to go back to our named vector. And let's see what else we could do. So if I click source, I'll see total votes again is exactly as you want it to be. But what if I wanted to sum up the columns too, to figure out for each voting method, how many votes did we receive? That is, for each poll and mail column, how many votes were there in those? Well, I could really just change my for loop. Instead of using row names, I could iterate over column names. So call names will tell me, if I go to the console, call names will tell me what columns do I have inside this data frame. And I could then change my loop appropriately. Instead of calling each column candidate on each iteration, I could call it maybe like voting method for the polling or the mail-in ballots. And then I could change how I subset my data frame. Instead of subsetting by row, I could subset now by column. like this, and I could then update the name of each of these elements to instead be the same name as the method we're counting. So pretty much the same idea, same flow, but just a different process across columns now. If I click source, I'll see in total votes that I've now counted up the total number of votes for each column. Okay. So it turns out that this method of doing things in R, this kind of analysis, applying some function for every row and for every column, is so common in R that we actually have some family of functions we can use to do that same analysis. And as we move from this world of writing procedures, that is, specifying a loop like this and specifying everything we should do inside that loop, to relying more on functions, we'll enter into this world called functional programming, where in functional programming we can actually use functions to do the work of iteration for us. Now, one common hallmark of functional programming is applying some function across these individual rows and individual columns. So R gives us this function called apply. And if I wanted to have the same result we just saw with our for loop, but now using this function, I could use the following syntax. I could use this function called apply and give it 3 arguments. The first one is the data frame to work with. In this case, votes, as we see here. The next one is one called margin. And margin stands for, do I want to apply this function across all of the rows or all of the columns here? When margin is 1, that means apply some function across all of the rows. When margin is 2, that means apply this function across all of the columns here. And then, finally, the third argument to apply is a function itself. And this is a hallmark of functional programming. We can pass functions as input to other functions. In this case, we're telling apply, here is the function I want you to use to basically work across all of these rows and all of these columns here. So when margin is equal to 1, what will happen? When I apply the function sum, well, for every row, I will get back a sum of every element in that row. When margin, though, is 2, what will I get? I'll get back the sum of every element inside each of these columns here, storing it, let's say, kind of at the bottom of our data frame here. So let's see this in action. I'll come back to RStudio here, and let's try to use these apply functions instead of doing things more procedurally, typing a loop and then everything I want to do inside of that loop. I argue I could actually write all this code in terms of a single function call using apply. Well, I want to apply this function on a given data frame, votes, as we just saw. I want to apply it across all of my rows, that is, for every candidate that I have in my data frame. And the function I want to apply is the sum function. I want to take all of these rows, and for each row, I want to sum up all of those values. Now, if I run this line of code on line 2, what will I get? The same exact result. I'll get now a named vector, Mario, Peach, and Bowser, these 3 elements here, with Mario being 100, Peach being 150, and Bowser being 120. Notice how, if I go back to my data frame, this is the same thing we had, where for every row, I've now found the sum, and apply has returned me the name of that row and the result of summing all the values in that row. Let's think about this too. What if I changed margin to 2? Well, this would find me the sum of every individual column, all the values within those individual columns. Whereas before we had to change row names to column names and change various other objects, now I can simply change 1 to 2 to work on columns here. Let me click source, and now I'll see if I go ahead and hit line 2, command enter, now I get back that same result, the names of each of my columns and the result of summing up all of their values here. Okay. So we've seen a much better way now to approach this same problem. Instead of doing things procedurally, writing a loop and saying exactly what should happen in each iteration of that loop, I can rely on a function like apply, do a lot of that work for me. And moreover, I can pass a function as input to apply for it to use on each iteration that it goes through in my data frame. Now let me ask here, having seen these apply functions and how they work, what questions do we have about them?
My question, instead of using the procedural approach of like sorting or unsorting, are there any like existing function that I can use it on the data frame for sorting the data in the rows like or columns?
A good question. So one thing you might want to do is sort your data. R just come with a function called sort that can do just that. Let me show you a little bit of it here. If I come back to RStudio, let's say I want to sort this vector I'm given from apply. I could call this vector something like total votes, just like this. And let me run line 1 and then line 2. Now I have total votes being this vector of named elements across my columns. Let's say I wanted to sort these. Let me say I could use the sort function here, and I could type total votes inside as the input to sort. And now, if I hit Command Enter on sort, I should see, well, it's kind of already in sorted order, at least going low to high. But now if I type !sort to see how I could change the order here, I might see that sort has this parameter called decreasing, which is initially false, which means that we're going to count up instead of down. But now if I want to sort going low to high or increasing order, I could set decreasing, if I want to set the vector going from high to low, let's say, instead of low to high, I could set decreasing equal to true, and then we'll see this vector is now in sorted order. I can do the same for every candidate that I have. Let me update total votes across the columns. Let me now, on line 3, run sort. And now I have my candidates in sorted order as well. So a cool trick if you want to sort your data, now using this sort function. And you can change whether it goes up or down using this decreasing parameter here. So we've seen a lot today. We've seen how to define our very own functions. We've seen how to write our own loops to repeat code multiple times. And we've seen how to combine these two ideas, dipping our toes into functional programming, that is, using functions to do the work of iteration for us. When we come back next time, we'll actually see how to clean up our data, how to tidy it, to make analyses like these even easier. All that and more next time. See you soon.